This is okay. Yeah. Thanks for inviting us. So last year I was here to talk about the reaction InCHI, and the reaction InCHI as such is a special InCHI that is handling reactions, and actually I'm representing a full group working with those and developing the reaction InCHI. And as you see, there's a new part in there represented by Istvan, and ChemAxon has now been represented in this group as well, which is a big progress because now we can discuss it on a broader scale, what we have to implement. But let's start with what is reaction InCHI and what I presented last year. The original idea of InCHI as well was how can we search chemical structures in the internet and vendor independent. And about, I think in the year 2000, the development of InCHI started, and somehow around 2010 it scaled up, and most of the databases have got an InCHI connector meanwhile. Slightly later, 2008, the discussion about reaction InCHI started. There was an reaction InCHI in 2011, which was a prototype, and the first release in 2017. But the major purpose was really, that you was able to have a string for searches in the net. So, what do we have to do? Just a short feedback, summary of what we discussed last year. We've got reactants, we've got products, and we've got any agents in a reaction that may be solvents, catalysts, and whatever you have over there. And we are just representing those guys in a so-called reaction InCHI, which is better represented as an example over here. This is very simple esterification, nothing particular. But what you see over here, you've got the acid as a catalyst, and those are the EDUCs, those are the products. And the reaction InCHI is set up in a way that you just identify the starting materials, and then you represent the starting materials in ascending order. So you start with the ethanol, then you continue with the acid as starting materials, and then you find this one over here. And continuing over here, you got the InCHIs of the products, so the ester and water. And last but not least, in the fourth section, you have the so-called agent, the catalyst in this case. Special over here, this is an equilibrium reaction. And quite interestingly, most of the formats do not handle equilibrium reactions up to now. And there will be some more remarks later on. OK, to make it searchable, the so-called InCHI key is pretty much used in a lot of searches for the internet. So we have a straightforward link to the reaction InCHI key, to the InCHI keys, by using the same format over here, but instead of the full InCHI, we are using the InCHI keys to let the reaction be recognized by those types of searches. Plus two more keys, and those two more ones are necessary first to index the entire reaction, so that you can really use it for comparison of different reactions or for the reaction search in the internet. But for that one, we have one more InCHI key, which we call web reaction InCHI key. That has come up out of the fact that you don't know sometimes how somebody sees, for example, the ethanol over here, because this is a solvent in that case. Yeah, so the real role of most of the components is sometimes not so clear, sometimes data dependent, sometimes just author dependent. And now we said, okay, we have one key that is only handling each of the components once to make it more searchable, and then you got a rough overview of the results, and then you can continue with the search in details. And now, Istvan, who has started to build a demo.
I would like to show you a few useful features in ChemAxon softwares which can help you working with reaction InCHIs. The first is for visualizing reaction InCHIs. This is a RInCHI from the presentation. If you have trouble to read it, you can import it with. You can import it with Marvin Sketch. Too many things on the. Okay, so you can import it with the Marvin Sketch, and you have a visual representation for the content of the RInCHI. It works vice versa. So if you have drawn a reaction earlier and you want to generate a RInCHI for this reaction, you can save RInCHI file, you can select it from the Save dialog. And you have a generated RInCHI string. Also, you can export the RInCHI key for the reaction for search purposes or such. And you have all the 3 types of RInCHI keys. If you have multiple files that you would like to convert to RInCHI format, you can use our command line tool called moreconvert. And I clear this out. And I have a few of the reactions in MRV format, and I can convert it to RInCHI format, and all of them are here. And to combine all together, if you have multiple RInCHI files, you would like to generate, for example, image for it for visual representation. You can generate images with moreconvert as well. It takes a bit more longer, but you can generate multiple images of reactions. These features and the reaction RInCHI support is available from 19.11 version of ChemAxon softwares. Of course, we would like to keep the reaction RInCHI support up to date and adopt any changes that developed and any improvements are developed by the RInCHI Trust and delivered for us. And to take a peek into the future and the improvements of reaction RInCHI, I give the stage back to Gerd, and he'll show you around.
So what's next? So the base is just the reaction RInCHI, and the reaction RInCHI is an identifier. So that's its major purpose. But of course, first, for the next release, we have got technical issues. But we are going to provide a number of additional information that we think have become necessary in the last discussions, and actually where we see the reaction as general go-to. So we need additional import and export formats. In the current moment, as seen from the reaction RInCHI side, so from the technical side, it's restricted to RxN files and RD files, and therefore for mol files. And of course, we have to extend it to reaction smiles and the new UDM format, which has been released as version 5.0 by the Pistoia Alliance now in November. Beside new formats, we are going to have so-called atom mapping. I'm not so sure if you're familiar why you need this atom mapping at all. Because if you think about a reaction, the point is that molecules do change, obviously. And some of the atoms do vanish, some others come into the game, into the new products. And what you have to do is that you need an identification where to find the old atom in the new molecule. And this is basically called atom mapping. On top of that, you see this types of marks, and they just indicate that the bonds are changing as well. Yeah, so besides the atom mapping, the original idea was to have a bond mapping as well, because for a long time I learned that you need bond mapping and atom mapping together to have a unique representation. So instead of just going through the files, let me just take the example. So you just saw this reaction, this reduction, and to have sure that we are having the atom mapping, we're just using the numbering schema that is given by the RInCHI itself. Yeah, so the blue numbers just represent the atoms, and we just now say, you know, that the first atom of the first molecule of the structures of the starting material side becomes the first atom on the production side. So all the products are marked with the 3 originally, or the starting materials are marked with the 2, And this sign is basically used in the reaction InChI to distinguish between starting material and the products. At last but not least, we don't need the 2s and 3s anymore, and then we can create one additional long string with that one. And we call this one aux info because this is not an identifier anymore, but this is basically just an additional information that is along with the reaction. Quite interestingly now, while we started to work with that one, we found out we don't need the bond marks anymore, because there's a big difference between the original RxN files and the new system. RxN files are not canonicalized. Yeah, so they are really depending how you draw them, while this system is canonicalized and you've got a unique number representation. And with this unique number representation, we had even examples that are pretty nasty for mapping in a unique way and unique representation. And this is one of the very nasty parts where I learned that I need bond mapping, where you just have to say, okay, this is actually the same compound, but what is really happening is that those bonds are just running around, and this is not a localized molecule, but you get those two versions in an equilibrium roughly about 500 degrees. And now with the new system, it becomes obvious that you've got a unique representation, while basically if you look into that one more explicitly, you just see the InChI representations are identical, so A goes to A, but the aux info makes it unique. So this is a very particular case, but comes up to an area where we would like to go to, and this is really that the number of the interest of automated synthesis is really growing up at the moment, and that you need automated pathway detection for that. And this is one of those pathway detections with in a diagram. And we would like to support those types of area with a few other additional properties. Pathway detections have been done, I think, for the last 30 years. They've never been so successful that it was really adopted by the industry. But now actually things are changing. And there are a few things I would like to mention over here. For a long time, there's something called class codes existing that just group additional similar reactions within an identical code so that you can do clustering, for example, to identify those ones in the big system. More recently, about 2 to 3 years ago, the University of Cambridge worked over over reaccess in that case, and identified something called procedural aux info. We are following those ideas. And pretty recently as well, Waller and Ziegler from University in Münster published a paper about Monte Carlo methods to identify multiple pathways within big databases, so mainly reaccess again, to get the best, the most optimized representation. So how are we thinking to handle that one? First, we have to identify those reactions that fail. Yeah, so failing reactions are very important information as well, because not to work into that direction again. Then for people who have licensed the class codes, we're just having this additional class code layer over here, so to make it available. And we're talking to Reaccess about a similar concept they have, which is called transform. On top of that, the next group is really coming to those papers I mentioned from the University of Cambridge that we call proc aux info. In that proc aux info, we are going to have the different conditions you run a reaction in: temperature, pressure, over time, whatever, and concentrations in one string representation. And we are working on that string representation in a way that you can use it for machine learning straightforward. Yeah, so it becomes a way to have an interactive further analysis of those reactions. And that's what I would like to present, because that's what we're really working on right now. And if you're interested in it, the download is available on the InChI Trust site. We published a paper about all of that. And in case of questions, don't hesitate to send an email. And a lot of thanks to all the people supporting us from InChI Trust, giving the money. Actually, we are a UPAC group, I found out. Those are the members, so especially for ChemAxon as well, who are just joining us with their